Okay, so new definition. Let G be a group and let A be a non-empty subset of the group G. The centralizer of the subset A in the group G is the set, which we denote C sub G of A, and this is the set of those elements G in the group such that G times A times G inverse is equal to A for every element A in the set A. Now, since G times A times G inverse equals A, if and only if G times A is the same as A times G, the centralizer of A in G is the set of those elements in the group that commute with every element in the set A. The centralizer of the entire group in itself is called the center of the group and is denoted Z of G. So as a corollary of the previous theorem, let G be a group and let A be a non-empty subset of the group. Then the centralizer of A in G is a subgroup of G. So proof. Notice that for every element in the set A, and there is at least one since the set A is non-empty, we have that identity times A times the inverse of identity, which is identity, is equal to A, where the identity element is an element in the set G. And so the identity element is in the centralizer of A in G. In particular, the centralizer of A in G is not empty. Now let X and Y be two elements in the centralizer of A and G. Then, for every element A in the set A, we have that X times A times X inverse is equal to A, and Y times A times Y inverse is equal to A. That is, for every element A in the set A, we have that X times A is the same as A times X, and y times a is the same as a times y. Now as y times a is equal to a times y, we can multiply on the left on both sides of the equation by the inverse of y, so that we have a is equal to y inverse a times y. Notice that this means that the inverse of y is an element in the centralizer of the set A in the group, since the inverse of y inverse is y. Now, since x times a is the same as a times x, and a is equal to y inverse times a times y, we can replace the a on the left-hand side of the equation with this expression involving y and its inverse, so that we have x times the quantity, y inverse times a times y is equal to a times x. Now, as these are all elements in a group, it is associative, so we can regroup the terms any way we like, so that we have x times y inverse times a times y is equal to a times x, or x times y inverse times a times y times x inverse is equal to a, multiplying on the right on both sides by the inverse of x. Now notice that y times x inverse is the inverse of x times y inverse. That is, x times y inverse is an element in the centralizer of A in the group G, and hence the centralizer of A in G is a non-empty subset of the group G, such that for every pair of elements x and y in this set, the product x times y inverse is also an element in this set. And therefore, by the previous theorem, we have that the centralizer of A in G is a subgroup of G. So notice that the identity element is always in the centralizer of A and G. Now, the centralizer of A and G is once again the set of all those elements x in the group, such that x times A times x inverse is equal to A for every element A in the set A. That is, the centralizer of A and G is the solution set of the equation x times A is equal to A times x, and this is an equation in the group G where the element A is in the set A, and this corresponds to a system of equations x times a sub 1 is equal to a sub 1 times x, and so on. For a sub I is an element in the set A. So this is particularly useful for finite groups. And in particular, for a singleton set, which is a subset of the group, the centralizer of the singleton is the solution set of the single equation x times a is equal to a times x, once again in the group G. Now again, this is a solution set. The identity is always in the centralizer, and so there is at least one solution, the trivial solution, that being the identity for this equation. Now this is not a linear equation in the group, and so we are not guaranteed a unique solution. And so the centralizer of a set A is the intersection of the centralizers of the singletons for the elements in the set A. Now notice that the centralizer of the singleton containing the identity is the entire group, since every element in the group commutes with the identity. So let's look at an example. So recall that the subset of quaternion units consisting of plus or minus 1, plus or minus I, plus or minus j, and plus or minus k is a non-abelian group under multiplication. Now the centralizer of the singleton containing the element I is the solution set of the equation x times I is equal to I times x in the group, which is the set containing plus or minus 1 and plus or minus I. In fact, for every singleton A, where A is either plus or minus I, plus or minus j, or plus or minus k, the centralizer of that singleton is the set containing plus or minus 1 and plus or minus a. Now for the centralizer containing the identity, which is 1. This is the entire group. And similarly, the centralizer of the singleton containing -1 is also the entire group, since for every element A in the group, you have that -1 times the element A times the inverse of -1, which is -1, is equal to A. And so the center of the entire group is the intersection of singletons, of the centers of the singletons. Correction, the centralizers of the singletons. And the only elements that each centralizer has in common is plus or minus 1. So next we'll prove a Lima. Every subgroup of an abelian group is abelian. It's proof. Let G be an abelian group. And let H be a subgroup of G. Then, for every pair of elements A and B in the set H, A times B is equal to B times A, since the set H is a subset of the group G, where that group is abelian. So as a corollary of this lemma and the previous corollary, let G be an abelian group, and let A be a non-empty subset of the group. Then the centralizer of the set A is the entire group. So proof. By the previous corollary, we have that for every non-empty subset A of the group G, the centralizer of A is a subgroup of G, and by the previous lemma, we have that this subgroup, which is the centralizer of A and G, is abelian. So every element of the set G commutes with every element of the set A, since A is a subset of the group G, which is abelian. And therefore the centralizer of the group, of the set A is the entire group G.